Hi guys, in the previous video I've talked about how we can use dimensional analysis to take out or extract what the dimensions of permeability might be. So in this video I'd like to talk about the definition of a Darcy, which is the unit that is used to define permeability. So to do that, let's first quickly construct a experimental setup again. So this is a medium through which our fluid will flow. Consider it as a cylinder filled with some kind of sand, which causes it to be a porous medium, and there is a fluid flowing through it with a flow rate of Q and a viscosity of mu, and this has the length L. It has a constant cross-sectional area of AC. It has pressure of P1 at the inlet and a pressure of P2 at the outlet. Alright, so let's quickly formulate what Darcy's law is. So Darcy's law is a law that describes the flow of fluid through a porous medium and was based on Henry Darcy's experiments of the flow of water through beds of sand. So it forms the basis of hydrogeology, which is a branch of earth sciences and has applications in petroleum engineering. So it is also analogous to Fourier's law for heat conduction, Ohm's law for electrical networks, and Fick's law for diffusion. Originally was determined experimentally, but it was later derived from the Navier-Stokes equation. Alright, so let's do a quick statement of Darcy's law. So basically it states that Q, which is the volumetric flow rate of a liquid or a fluid through a porous medium, is proportional to the pressure difference, or we can just take that as delta P, over the difference in length. So this was later can be rewritten as Q is proportional to dou P over dou L, which is just describing the pressure gradient of the fluid. So we know later, through the work of Morris Muscat, that this can be generalized even further as follows. So Q is equal to K, which is the variable that we are interested in, K over mu, multiplied by the cross-sectional area AC, which we will just write as A for simplicity, multiplied by dou P over dou L. If I remember the colors correctly. Alright, so in order for us to find out what the units of permeability are, let's first rearrange this equation to have K on one side. So K is going to be equal to Q mu. I used the wrong color for mu there, didn't I? No worries. Just going to draw over that. Multiplied by the cross-sectional area, which will be constant throughout the entire medium, multiplied by the pressure gradient, which is dou P over dou L. Great. So now let's list out what the units that are used to define 1 Darcy are. So first of all, we know that Darcy permeability is defined in Darcy's. So 1 Darcy. So what is 1 Darcy's of flow? So well, if we consider the experimental setup just now, when we have a flow rate of 1 cubic centimeters per second of a fluid with a viscosity of 1 centipoise flowing through a cross-sectional area of 1 square centimeter over a pressure gradient dou P over dou L, which is equal to, so since this is a combined unit, I'll just be using white, of 1 atmospheres per centimeter. So again, let's go through that again. It's a bit of a mouthful, but when we have a liquid or a fluid with a viscosity of 1 centipoise flowing at the rate of 1 cubic centimeters per second through a medium, a porous medium, with a constant cross-sectional area of 1 centimeter squared through a pressure gradient of 1 atmospheres per centimeter. So all of these conditions hold true if the permeability of the medium is exactly 1 Darcy. So let's find out how we can find what the value of 1 Darcy is. So from the previous video, we know that the dimensions of the Darcy are centimeters squared, are length squared. So we'll be able to express Darcy's in terms of area, or in terms of some unit of length squared. So let's have a look. First, let's quickly rewrite this. So K is equal to Q, which we're going to be writing as 1 cubic centimeters per second multiplied by mu, which is 1 centipoise. Now, before I write 1 centipoise, I want to acknowledge that it is equal to 1 millipascal seconds. So I'm going to write 1 milli. Milli is just 1 times 10 to the minus 3 Pascal seconds. Let's put a dot over here. Over the cross-sectional area, which is 1 centimeter squared, multiplied by 1 atmospheres per centimeter. Alright, so we're already pretty much on our way. Initially, when we look at this, we can immediately cancel some things because we have some centimeter terms, we have some second terms. So let's begin with some cancellations. We'll use pink to cancel things out. So these seconds cancel. This is a centimeter cubed on the top, a centimeter squared on the bottom, and 1 over centimeters over here. So all of these can simply cancel out to centimeters squared. So now we're just left with some units of pressure, pascals, and also some units of pressure over here. Now this is where we can recognize that 1 atmosphere is the same as 101,325 pascals. Alright, so we can simply rewrite this as follows. 1 atmospheres is the same as 101,325 pascals. So this way, the atmospheres cancel out each other, and now the pascals cancel out each other. So there you have it. The definition of the Darcy, of 1 Darcy specifically, is, so now I'm just going to be writing everything in lime. It is 1 times 10 to the negative 3 over 101,325 square centimeters. That's great. So if you punch this into a calculator, and you guys probably want to memorize this if you're taking petroleum engineering or hydrogeology or anything, any field that uses this equation or this law, this comes out nicely to, where's my line? It comes out to 9.869 times 10 to the negative 9 square centimeters. Oh, that's cute. Great. So now we can rest easy knowing that we have been able to derive a value for 1 Darcy. So we can stop here, or we can go just a little bit further. First, let's recall that in field units in the petroleum industry, we typically use millidarcies as our field unit of choice. So these are the standard units that people in the industry use. So 1 millidarcy is the same as 1 times 10 to the negative 3 darcies. So that can just be rewritten as 9.869 times 10 to the negative 12 centimeters squared. Now, if you wanted to write that in terms of meters squared, well, that's also fairly simple. Just write that down again. Centimeters squared. Now, there are 100 centimeters in a meter, and you have to remember that this is centimeters squared, so you have to square all of this. So what will happen is that the centimeters squared will cancel out, leaving us with only meters squared. Alright, so that would be, oh my bad, there should be a 12 here. Okay, so that would be 9.869 times 10 to the negative 12 divided by 100 squared. So this will be 9.869 times 10 to the negative 16 meters squared. Alright, but what if you wanted to express that in terms of feet squared? Well, there's a few ways you can go about this. Since I personally prefer to go from here. from the centimeter squared definition. This is because I can make use of the fact that 1 foot is equivalent to 30.48 centimeters, and it's nice and round. So let's just rewrite that. 9.869 times 10 to the negative 12 centimeters squared. So I know that 30.48 centimeters squared is the same as 1 foot squared. Sorry, I should put this square sign on the outside. So again, these centimeters squared will cancel, leaving us with feet squared. So I don't know what that is off the top of my head. So I'm going to pop that in my calculator real quick and see what we get. Okay, that gives 1.0623 times 10 to the negative 14 feet squared. So there you have it, the units of 1 Darcy, as well as some common ways of expressing the common field unit, which is the millidarcy in terms of centimeters squared, meters squared, and also feet squared. I hope you enjoyed the video. If you liked it, leave a like, comment, and subscribe, and click the bell icon to get notifications. Thank you, and stay tuned for more.